Hello there. Welcome to another session on learning statistics. This is Harjit Singh, and I'm going to walk you through today on various aspects of statistical sampling, the Central Limit Theorem, and several other associated topics. So the learning objectives today include learning about sampling populations, discussing why we sample populations and why we describe those populations. We will look at four methods of describing sample populations, like simple, random, systematic, stratified, and cluster sampling. We will also look at the sampling error, what it is, and how to understand and how to consider this. We will also look at sampling distributions and go through Central Limit Theorem, which is very, very popular in the world of statistics. And we will compare how sample mean and population mean, they play together. We look at point estimate versus confidence interval, and the related topics like when to use Z values, Z statistic or T statistic related to confidence interval. And other related topic is sample size. Sample size, large sample size versus small sample size, we will look at it. Reason for sampling a population. So why do we need to sample? I use sampling. There are several practical reasons why we prefer to select portions or samples of a population. We have to observe and measure when studying the various characteristics of a population. Sometimes the items in the population are so many that it's practically impossible to observe and study everything. And sampling saves time, money, and resources. It is because it is practically impossible to sample entire populations, considering there are a large number of items in a population. Let's look at various sampling methods. Simple random sampling. In this, each population member has an equal opportunity or equal chance of selection. Then we have a systematic method. A random starting point is chosen in this, and then every kth, after, let's say, 6th or 7th, every kth member is selected after that, right? Stratified, in this, population is divided into groups, and groups we call, the other name of the group is strata. Strata is name for the group. So we divide into groups or stratas, and random samples are taken from each of them. Okay. Finally, we have the last method is cluster sampling. In this case, a population is divided into clusters, and samples are taken from those clusters randomly. When we randomly select clusters, and then we take samples from them. Okay. Now let's look at these methods one by one. Simple random sampling is by far the most widely used because it's very simple to use. And in this case, every item in the population has equal probability or equal opportunity or equal chance of being selected. Okay. So in this case, the consideration is that in an unbiased sample, so it's a simple random sampling with unbiased sample, all members of the population have a chance of being selected to the sample, equal chance. If the population is small, relatively small, then one could place all the items of interest in a box and select the sample. It's easy to select when you have a very few items in the population. When you have a large number of items in the population for large samples, I mean, if the population contains too many items, then it's hard to study the entire population. You have to use sampling. So simple sampling is like where you randomly select the members of the population into a sample, and every member of the population has equal chance of being selected. Okay, so let's look at this example. So it says that you have a population of interest is 750 Major League Baseball players on the active rosters of 30 teams at the end of the last season. Sorry. A committee of 10 players is to be formed to study the issue of concussions to make sure each player has an equal chance of being selected. Use a table of random numbers. So like say this is the random numbers can be generated with some software, computer. You can Google search, and there are many free tools available to generate random numbers, right? So this is a sample table of random numbers. Okay, so we have a total 750 Major League Baseball players. That's the population. A committee of 10 players to be formed, sampling, to make sure every player has an equal chance of being selected. Use a table of random numbers. So okay, so number one we do is prepare a list of all the players and number them from 1 to 750. because we have total 750 players. So we start from 1 and we label them 1 through 750. Now, second step is we need to randomly pick a starting place. So we need to we need to start from somewhere, right? We have to use the random numbers table to start from somewhere, and then we have to select 10 3-digit numbers. That's the problem asking for. So because you know that the highest number the label, because we have total 750 players, so 750 is a 3-digit. So we have to find 10 3-digit numbers because sample size is 10. How we do that? So you can simply randomly just look at the table and where your eyesight goes there, pick something like 3-digit number. So here, for example, we got this 037. That means 37, right? 037, 3-digit starting point. Because this number falls within 1 to 750, so it's a valid number. We keep it. Then we can assign this to first player. We selected randomly. Then second player, we can go this way, just randomly, any direction actually. So let's say we go right hand side, the same row. So here we have 447. Then compare with the limit here. So 1 through 750. Does 447 fall within 1 and 750? Yes. So this is a valid number. We keep it. And we go to the 961 here. 961 is 961 fall. Is it within this range? No, it's bigger than the max number. So we discard it and go to the next one. 784. This is also bigger than 750. So we discard that also. So we go to the next one. 189. And that is okay. That falls within this range. So we can assign this to third player. So we can continue like this until we have 10 of these 3-digit numbers selected, and we can assign them to 10 players in the sample. And this is example of random sampling, simple random sampling. Okay, second method was systematic random sampling. So what happens in systematic random sampling? In this case, again, we have to sample because we do not have a list of entire population to begin with. But we can, what happens in this one is a random sample, systematic random sample. In this case also, we select the starting point the way we did before, right? We select it and then we pick like every so often, like every kth number. K means 5 or 6 or 7, every 6th number, 5th number, or 7th, whichever you pick, interval. So you have a system, it's a systematic approach. You, let's say you start from 5th person, and then say after that, every 10th person you keep picking, right? So, and that's a systematic random sampling procedure. So his example here about this grocery store, Studs grocery store wants to study the length of time customers spend in their store. Okay. So to study that, he randomly selects the days of the week, the times and the starting point of the study, then systematically select the customers and measure the time each spends in the store. So how we do that? Okay. So as you know that there's so many people come to store, and you can't study every single person. So you need to use sampling. So what we do, like you can use systematic random sampling. And so what you can do is you can, let's say, select 100 customers over 4 days, right? 25 people in one day you can sample, right? 25 customers. So you can have like different times in a day allocated for sampling. Maybe let's say 8 a.m., 11 a.m., 4 a.m., 4 p.m., and 7 p.m., for example. Okay. Then you can write the 4 times and 4 days on pieces of paper and put them in 2 baskets. Okay. One basket for the days, other one for the times of the day. Okay. Then select one paper slip from each of those baskets. So what do you get? You get the first set of first pair of day and time. Okay. Let's say, for example, you got like a Tuesday. You got Tuesday to start your sampling process on Tuesday, and let's say your time you got was like 11 a.m. Right? So then you can start just guess. Let's say, for example, okay, you can select the 5th customer who comes into the store as a starting point. After that, you can select every 10th customer. So initially, okay, you had a 5th customer. So after that, 5 plus 10, then 15th customer, and 15th plus 10, 25th customer, 25 plus 10, 35th customer. So that way, every 8th or every 10th customer you are selecting to to study. Okay, and you continue to do that until you reach the daily requirement of 25 customers that you need to study. You and continue this way for 4 days until you finish studying 100 customers. And this is an example of systematic random sampling. Okay, now let's look at the stratified random sampling. So what is stratified? As I said before, that a population we divide into groups we call stratas, and then we randomly select elements from each stratum, each group, basically. So example here is a study of 50 of the 352 largest US firms ad spending. So we have to begin by identifying or forming strata or group, then use random sampling within each group based on relative frequencies to collect the sample. Okay, so let's use this data that's given to us here. So we have how many groups or how many stratum? 1, 2, 3, 4, 5, right? Total. And then we have probability return on equity. So that's profitability. I'm sorry, profitability. That is a 30%. So different groups have different profitability, 30% and more. 20% to 30%, 10 to 20, and 0 to 10, and then negative deficit. Okay, then how many firms belong to each of these groups? So we have 8, 35, and so on. And because we know there's a number of firms, like they fall in different groups, we can calculate the relative frequency by dividing number of each firms with the total number here. So like 0.02 we found by dividing 8 by 352. And similarly, the second entry here, 0.10, we divided 35 by 352, and so on. And total frequency, when you know that we relative frequencies, when we add for all the groups, it should be 100%. So 100% means 1. So we have 1 here. Okay. And right, so this is like a sample size, number sample. So we use this. So how we do that? Let's take a look. Sorry. Okay. So this is you know, how we use. Let's see how we use this actually. So what we have, this table given to us, and we have to look at which strata has like a high probability of, I mean, the firm from which group has high chance of being selected versus other. So if you look at the relative frequencies here, you see that third and fourth strata, when you know, these two groups have like a highest level of relative frequencies. So if you add them both, actually, the both constitute 0.87%. You add them up. So there is a high chance of selection from these stratas. And the other stratas like 1, 2, and 4, they're very tiny. So it's only 0.13 when you add them up. And we may get the elements from these stratas, but the chances are very low. Okay. And let's say now we have 50 firms are selected for study, that we say a study of 50 firms out of 352. We can find out based on the probability. Okay. So what is the probability that one firm will be selected from first group? Okay, what is the probability that one firm will be picked from first group? So we look at the relative frequency for that firm, which is 0.02, I mean, for that group, and we multiply that by the sample size, 50. So 50 times 0.02, and that gives us the probability of selecting one firm from this group. Okay, and similarly, if we look at another one, which is 0.10, the second entry here, second strata or second group. So what is the probability that one firm will be selected from this? So 50 times 0.1. Okay, 50 times 0.1, and which gives us so number of samples. So this is the probability, 5 of them, right? So basically, you multiply with the sample size to find the probability of selecting something from that strata or group. Okay, and you know that when the relative frequency is higher for strata 3 and 4, the probability of selecting a firm from these groups 3 and 4 is very, very high. This is a stratified random sampling. How about cluster sampling? So cluster sampling is used, as I said before. So you divide the population into clusters, and then you randomly select members of the clusters. I mean, randomly selected, not all the clusters, but you randomly select the clusters, and then you use the random sampling from within each cluster. Okay. So here's an example here. Say, hey, we suppose we wish to sample residents of 12 counties in greater Chicago area about their views on government policy. Randomly select 3 counties and then select a random sample of the residents in each of these 3 counties. Okay, let's see how we do that. In this case, we have 12 counties and we need to select 3 counties and then select random sample out of them, right? So it's pretty straightforward. Basically, if you try to, draw a sample from all 12 counties in greater Chicago, it will take very long time and it may not be practically possible. So randomly selecting 3 counties and drawing samples from them, that's more effective. And you can first form these clusters and then use random sampling to pick the residents for the sample from these 3 counties. Okay. So it's a combination of cluster sampling and a simple random sampling. Sampling error. Sampling error is the difference between sample mean and sample mean and the population mean. Okay. Ideally, what we want is we want the sample mean to be same as population mean, which means that sample represents population perfectly. But it's not always the case. Actually, there is sometimes there is a difference, and the difference is called sampling error. For example, this is an example of some hotel or inn, the rooms rented in June. The mean of the rooms rented is 3.13, and then they took 3 random samples of the size 5, and they found that the means for those 3 samples were 3.80, 3.40, and 1.80. So sampling error is the difference between this population mean and each one of these. Okay, so 3.80 minus 3.10, that's 1. Then it is 3.40 minus 3.13, and 1.80 versus 3.13. So that's how we find. So 3.80 minus 3.13 gives us 0.67. That is a sampling error for that. And then when we subtract the 3.40, and we subtract the 3.13 from 3.40, we get 0.27 as sampling error, and so on. So we have like a multiple samples, and we find their means. We can plot those means also. So we can have a sampling distribution of sample means. Okay. So sampling distribution of a sample mean. So you can find all the means of all samples, all possible sample means, right? And then we can plot them, right? So the mean of the sample mean is exactly equal to the population mean, because it is supposed to be like this. There may be sampling error, but with plus minus, the mean of the sample means is equal to population mean. However, there is a difference here. The shape will look similar, but dispersion of sampling distribution around the mean will be narrower compared to the distribution of the population. They will be bell-shaped curve. They will be normally distributed, but the dispersion of a sampling distribution of a sample means will be narrower. So let's look at this example to illustrate that. So you have this starters industries have 7 production employees. The hourly earnings of each employee given in a table here. So we have 7 values here. What is the population mean? What is the sampling distribution of the sample mean for sample size of 2? What is the mean of sampling distribution? And what observation can be made about the population and the sampling distribution? So let's first find the population mean. So this is all given to us. So basically, this is our population. Population means the whole thing. What we have in the population, we have 7 elements here. Okay, 7 wages basically. Right? These are 7 earnings for 7 people. So population mean means mean of all these. So we can find, so this formula population mean is sigma x, all the numbers added up by a total number. So we have, you add all these numbers and then divide by 7, we get 15.43. That's the mean earning in the population. Okay. So we got now we need to look at a sample. So we need to look at sample size. Sample size is we have to divide. We need to using these 7 people actually. We need to pair them up in a size of 2. Okay, unique pair. So how we do that? We can create this table with the pairs. You can see Joe with the Sam, Joe with the Sue, and so on. All these people are paired like a pairwise, grouped pairwise. So total we got is how many? 21 total pairs. And we list the wages of these also here, and we can add them up and take a mean. Mean means half of this total sum gives us a mean. So we got 25 means for 25 samples here of 2 people each. Now we have to find sample mean. So how we find it? Like, so we have a sample means. We need to look at how many distinct values are there in this 21 collection of 21 samples, and how many times they occur. So we have it 14 happening 3 times, 15 9 times. If you look at this table here, 14 1 2 3, so 3 times, right? Yeah, 3 times. So 14 happen 3 times, and 17 happens 3 times also. So 17, let's see, 1 2 and 3. So similarly other ones also, 15 happens 9 times, and 16 happens 6 times. So these are the number of means. Total add up to 21. We can find the probability by dividing each one of the frequency of each with the total frequency. With relative frequency means probability. 3 divided by 21 gives us this 0.1429, and so on. And we can find the mean of all these samples also. So we add all these samples, all these we add them up, 21 of them, right? Then we divide by 21 to get the mean of the samples. Samples mean, it's the mean of the samples mean, 15.43. So what did you find here? So 15.43 and which is equal to the population mean, right? So that's what we are looking for. So that means the sample is a perfect representative of the population. So it's equal to, so mu is equal to mu x bar. We sample, the mean of all the sample means is equal to population mean. And but again, the spread is for samples mean is less than the population. If you look at this, the spread, because we have the max value, the max value in the samples is 18. If you see the 18 here, 18, right? 18. However, the max value in a population is what? Sorry, max value is population is 18 here, 18, right? Minimum is 14 and max is 18. So spread is between 14 and 18. However, for samples, we only go up to 17, right? So if you look at this graphically, see this in samples, we only go up to 17, but here we go up to 18. So this is narrower sample, the distribution of the samples mean is narrower than the population means, right? So that's the observation. Now let's look at central limit theorem. And central limit theorem is really useful in various statistical calculations. No, there is what it is. It says that if all samples of a particular size are selected from any population, the sampling distribution of the sample mean is approximately a normal distribution, and the approximation improves as large samples. So it depends actually the sample size, right? So if the population is normally distributed, okay, then any size, any sample size you choose, even if it's small, like a 10, even as small as 10, then the sampling distribution also will also be normal, normally distributed. So if population is normally distributed, then any size of a sample will be normally distributed too. However, if a population is not normally distributed, so it's then what happens is then you need a bigger sample to see the normal distribution. You need to have minimum size of sample should be 30 to observe the shape to look like normally distributed, the bell-shaped curve. Okay, so that's the difference. Idea is to find the central tendency here. So when something is normally distributed, it's easy to find the central point. Otherwise, if it's skewed, then it's harder. So you need to have bigger sample for that. So sample, now various considerations are related to central limit theorem. So the mean of a distribution of sample means will be exactly equal to population mean. Okay. So this is what we conclude, that because we are saying that the sample is a representative of population. Okay. And the standard deviation is given by sigma, and a standard error of the mean in this case is we call sigma x bar. Is formula we have is sigma divided by n square root of n, and the standard deviation of the sampling distribution, we call it a standard error of the mean. So standard error of the mean, this is the formula for that. Okay. In this case, like we observed before, that dispersion of the sampling distribution of the sample mean it will be, there will be sigma x bar times square root of n. Okay. Population dispersion is measured by sigma, whereas sampling dispersion is measured by product of sigma x bar and n square root of n. So, and this is something you need to remember, that if population is normally distributed, then sampling distribution of a sample means will also be normally distributed. It doesn't matter what size sample you have. And this is something that we observed before. We were talking about a central limit theorem. If the population is not normally distributed, and it's not perfectly perfect symmetrical bell-shaped curve, it's skewed to one side or other side, then you need to have a sample size of at least 30. Okay. So if population standard, there are conditions here. So if population standard deviation is known, so in one case you have the population standard deviation. In one scenario, other scenario, you do not know the standard deviation for the population. If you know it, the formula that you use to find that the z value is this one. So x bar, which is sample mean, minus the population mean, divided by sigma, divided by underscore n. N square root. So here z, what is z? So z is used to find the population parameter within a sample. Okay. So z helps you find the population parameter within the selected sample. And if a standard deviation is known, then you use z values. And this measure or statistic is called t statistic if a standard deviation is not known. That's the difference. All right, so let's take a look. Here it says that the Quality Assurance Department of Cola Incorporated maintains record regarding the amount of cola in jumbo bottle. Basically, what it is, they have a bottle filling plant, and the mean is 30.2 ounces, with standard deviation of 0.4 ounces. So a sample was taken with 16 bottles, and they realized that the mean of the sample was 31.38 ounces. The question is this okay? Is this acceptable or not? So sampling error here is 0.18, because if you plot this like this, you see that the mean is 31.2, which is accepted mean, but the sampling mean is like a 31.38, and you take the difference. So 0.18 is a sampling error, difference between the two. The mean difference between the sample mean and the population mean is the sampling error. Is this normal? Well, when you find the z value first. Z value is found by this formula you saw before, and this x bar is the sample mean, we 31.38 minus the population mean, and we fill in the values here, you get 1.80, right? So 1.80, and we can use the tables, z tables. There are z tables available online or in the back of the books, statistics books. That will give us this shaded area, which shows that there is only 4% chances, less than 4% chances, which is like a 3.59. So less than 4% chances that this could happen. So that means the conclusion is that this is not right. So they need to find out the reason for overfilling the bottles and need to fix it. So point estimate. A point estimate is again identifying a statistic to find the population parameter in a the quest is to find the population because when you have a sample, whether it's a point sample or interval sample, idea is to find a connection between sample and population. So when you use a single point or single value, then we call it a point estimate. Okay. And now look at this here. So here the example. Suppose the Bureau of Tourism for Barbados wants an estimate of mean amount spent by tourists visiting that country. They randomly select 500 tourists as they depart and ask the tourists about spending while there. The mean amount spent by sample of 500 tourists serves as an estimate of the unknown population parameter. So how to find it? So you can use the mean amount spent by them. That will give you idea. Actually, it's hard to study every tourist actually. So basically you are using a sample, and sample, and that will give you, look at the sample mean, and that will give you idea about the spending. Now, point versus interval. So confidence interval. So again, this is like a range within which a population parameter is expected to be there, because we are trying to look for the connection of a population to the sample. Okay, so how confident we are that we can find the value related to the population within the sample. All right. So the way this is defined is a range of values constructed from sample data so that the population parameter is likely to occur within that range at a specified probability. The specified probability is called the level of confidence. So that's why it's called confidence interval. Okay. So various factors we have to consider here. We have to consider number of observations, like a sample size, and standard deviation, dispersion, and level of confidence. The formula, again, if there are two conditions: if standard deviation is known, or if it's not known. If it's known, then we can use this formula for confidence interval, right? When population standard deviation is known, and then we can use this in the next example here. Let's say find the value of z, and when sigma is given, when standard population standard deviation is given, the parameter that we can use is a z parameter, z value. If it's not given, then we use t value. So here 95% confidence interval that we are interested in, and so how we use this? So we use this, we divide, because it's normally distributed, so we divide into by 2, and so anywhere ignore this shaded area, but within this shaded area, this area here, that is the confidence interval. This is 0.9 or 95%, 0.9500. You divide by 2, get the 2 halves here, right? And now we can use one of these halves values in a table here, the z table, and find out the value, the z value corresponding to that. So look at this here. So we have 0.4750, and go up and go sideways. We got 1.9 here and 0.06 here. So basically 1.9 plus 0.06, it makes it 1.96. That's the value of z. So we are interested in the interval minus 1.96 to 1 plus 1.96. That's our confidence interval for 95% confidence. Okay. So we can use this to solve a problem here where you have 49 managers. They have a sample mean of this salary, the income of them, and then standard deviation is 2050. Then say, hey, what is the population mean? What is the estimate of population mean? What is the reasonable range of values population mean, and how to interpret? So we know that we have the standard deviation is given to us, so we can use z value, z parameter, and we have the mean also here, so we can use this formula here for the 95% confidence interval. Sorry, confidence. So sample mean is given to us, and we know the z value is 1.96, and we fill in the values here, we get this answer. So that means mean plus minus 574. So interval is like when you on one side you add 574 to the mean, and other side you subtract it. So confidence interval is between this value and this value, and the number 574 is called margin of error, right? That's how we use it. If sigma is unknown, what we do that, sigma is unknown, population standard deviation is unknown. In that case, we use t parameter, t statistic, and the formula for to find confidence interval using the t value is this. Okay, so here here's the question, example question related to that. The dean of school, dean of business college wants to estimate the mean number of hours full-time students work at paying jobs each week. He randomly selects a sample of 30 students, asks them how many hours they worked last week. He can calculate the sample mean, but it is unlikely he would know the population standard deviation. So standard deviation of the population is not known. So how we can use then t relationship to solve the problem. Again, if standard deviation is known, then use z distribution. If not, then use t distribution. Okay, and there is a characteristics of a z versus t. T distribution is more flatter. They're both normally distributed. Z is not as flat as t. The spread is more, and t distribution uses degrees of freedom, which is equal to n-1, where n is a sample size. Okay, finding the value of t here. First of all, the basic assumption is that the population is normally distributed. Okay, but we don't know the standard deviation of the population. So again, confidence interval, assume that it's 95% confidence. We have to find degrees of freedom, which is n-1. Let's say sample size is 10. So 10-1 is 9. So we got this. This table is available in online or in the statistics books. So 9 and we have 95% confidence we are looking for. So we go and find the cell here. So 22262, right? We can use this value in the upcoming question here. In this case, we have a sample of 10 tires. Driven 50,000 miles, revealed a sample mean of 0.3 inch of tread remaining, the standard deviation of 0.09 inch. So we have to use 95% confidence interval, and we need to look at it. Is it reasonable for the manufacturer to conclude that after 50,000 miles, the population mean of amount of tread remaining is 0.30 inch? So we need to look for actually whether the interval we find if 0.30 falls in that confidence interval. So we're going to use this value, this relationship to find the confidence interval, because population standard deviation is not known to us. So we found that the interval is 0.32 plus minus 0.0664. This value is a margin of error, and then it gives us the interval 0.2562 to 0.384, and we know that 0.30 inch falls into that. So this is true. Okay, and confidence interval for proportions here. If they're asking about like a sample proportion of the population, in that case, if we denote proportion by p, sample proportion is equal to x by n, right? So we can use this formula. It's pretty simple formula to use. All right, so again, this is continuing with the confidence interval for proportions. Proportion, first of all, in this case, we looking at the binomial conditions here. Binomial, we have the values n pi and I men's pi. The condition is that both should be greater than or equal to 5. So we can use this formula for finding the confidence interval for a population proportion, this formula. And this is another question related to this formula here, where we have 95% confidence interval. We have what do you call? We need to find actually whether we have enough majority to approve the merger of the companies. And sample is 2,000 current members, and 1,600 plan to vote for the merger. So do we have enough majority to approve the merger? So we can use this because if we have the proportion here, P is equal to X by N, we know 1,600 out of 2,000 total, we got 80%, right? 0.80. So we're going to use the formula to find the 95% confidence interval, which gives us a 0.80 plus minus 0.018. So when we solve this, now we got two endpoints here, 0.782 and 0.818. And we know that we are looking for at least 3/4 of a majority, and 75% falls within this range. So yes, we do have a majority to approve the merger. So that's how we use proportion, sample proportion in statistics. Okay, so that was all about today's session. I hope you enjoyed it. I see you in another session like this. Thank you so much. Have a wonderful time.